So please join me to welcome Dr. Yoerger.
Thanks everybody. I'm happy to be here. See some of my old friends and shipmates, and certainly all my friends back at Hui send their regards. What they all found out when I was coming up here. Okay, so this talk today was a little bit inspired by if you read papers in the straight robotics literature, and someone from the sort of mainstream robotics community is starting to get into making a marine robot, they have these very vague statements about, well, we need robots to explore the ocean. Well, what do you mean by that? And they reply, well, you know, the world is covered 71% by ocean. And we're like, yeah, we know that. So I when I give talks to those communities, I try to flesh out what is it that we actually do? What are the questions that we're using robots to investigate that we've been successful with in the past, and which ones do we want to get better at in the future? So that's kind of the origin of this particular talk. If my clicker doesn't seem to want to work, so we'll just do this. Somehow that doesn't want to work. What do we got here? Okay, well, most of you know what the Woods Hole Oceanographic Institution is. Hui, we operate two large ships, the Atlantis and the Armstrong. The Atlantis being the host ship for the submersible Alvin, and we have 5 academic departments with about 1,000 employees, annual budget of about $300 million, at least this year. Okay, let's push the button again here. I'm still not having any luck. Okay, well, you know, marine robots, they come in a lot of shapes and sizes. You know, we have gliders, we have, this is a famous Remus vehicle being stalked by its prey, the white shark. Some fanciful, so bio-inspired vehicles. This one thinks it's an eel, and this one sort of thinks it's a fish. I have strong feelings on those topics, but we can leave that for another day. Deep sea robots, when I first started actually at the end of the 70s, if you can believe it, working in this field as a grad student, I have to say that robots were very much a curiosity. They weren't any sort of a workhorse standard things. ROVs were just beginning to appear for commercial work in the military. But since then, of course, now they're really a mainstays of science. And for the kind of vehicles that we work on, the cooperation between oceanographers and engineers is really the key to making these things useful. And of course, we're seeing an explosion in autonomous surface vehicles. And one of the great things is we have some of the world's experts here in the room. And one of the great things about this kind of type of robot is the design space is enormous, okay, in terms of how they're powered, what they can do, what their endurance is. I mean, I have a friend and he makes ASVs that can literally surf waves like a surfer, which he is, Peter Tchaikovsky, and he'll do surveys in like a foot of water, okay? Well, so they're literally all over the place. Drix, of course, is diesel powered. Something like the Mayflower or its sort of less fanciful follow-up, the Oceanus 12, is a diesel-electric hybrid. And then, of course, we have the environmentally powered ones. All of these vehicles have different strengths, and so they match up to the science programs that take advantage of that. But and this is my view, and this is a horribly wordy slide, but what are the problems we want to use robots to go after, obviously? How does the ocean circulation change? That's a big one. Plate tectonics, how does the Earth work? The midwater ocean, largest biome on Earth, okay, largely unexplored, and plays a critical role in climate. Critical ocean habitats like coral reefs are under threat. The seafloor is basically the world's biggest museum, okay? Shipwrecks, sunken cities in some cases, and I've been privileged to do some work in that, which is really great. And finally, we've participated in forensic examinations of modern ships and helped shed light on why they were lost. So these are the kinds of things that we've been using vehicles for. I don't think I need to belabor this point with anyone in this audience, but this is obviously a huge scientific problem and one where robots are making a huge contribution, specifically the Argo program. If you're interested in robots and you're interested in the ocean and you don't know about Argo, you should go Google it and get smart, because it's been fantastically successful. Thousands of floats, thousands of papers written, open data, beautifully maintained and operated data system. And I think a lot of those 5,000 papers are written by people who are in no way, shape, or form an insider in the community that produced those devices. And to me, that's the highest compliment you can have, when your data is so obvious as to what it is, it's easy to use, and it's curated. And so this has just been a tremendously successful program. The standard routine is, I think it's about 2 weeks. It goes down to 1,000 meters, drifts for most of that time, then it goes deep, it comes back up, and sends its data back. They are also used in many other very interesting ways. One of the most creative being, there's a version called the Alamo float, which are thrown out of the back of hurricane hunter planes. And they lay them down in like a picket line in front of the hurricane, and then they watch the hurricane. But rather than doing a 2-week cycle, they do like a couple-hour cycle. So they're just profiling as fast as they can. Fantastic, fantastic data. And there's a great Hui video, you'll see a little scrap of it later, where one of our joint program students is in the back of a hurricane hunter throwing the float out the back. Pretty cool job for a grad student, I think. And of course, the data that's come from this is just one of those 5,000 papers. Okay, the global average ocean temperature anomaly over time, it speaks for itself. So, robots are changing how we see the world. And of course, plate tectonics, one of the great, discovery, I was gonna say invention, of our time. When I was in junior high, we were told that South America and Africa, even though it seemed like they fit together, that was some kind of an illusion, okay? But all the 8th graders knew the truth, right? It has to be connected. Okay, so when I first started, this is what we were using robots to investigate, specifically seafloor spreading, mid-ocean ridges, and I spent a lot of time there. So going back before my time, of course, Ballard's Angus located the first hydrothermal vent, depends on who you ask, if you're from Scripps or Hui about that, but, and then based on the images and the acoustic navigation, they vectored Alvin into the spot. Don't let anybody tell you Alvin discovered the vents, no. And we actually have that debate, I go, look, if I showed you a picture of something, and I gave you a magical navigation system that let you find your way right back to there, and you got there, would you say you discovered that thing? I don't think so. But anyway, the teamwork of the unmanned system, the uncrewed system, and the human-occupied system is a great theme through everything I'm going to be showing you today. Typically we find things with the uncrewed systems, and then we follow them up either with a remotely operated vehicle or with the HOV. Now this is a vehicle called AUV, the Autonomous Benthic Explorer, which we started building in the 90s. It was the first vehicle I worked on to go in the deep ocean. And this is some results from a cruise that we had in 1999 that was critical because it really showed that AUVs could make maps of these spreading centers at great depth, a couple thousand meters, and show geologists things that they'd never seen before. At that point, Abe was considered by many scientists to be an expensive piece of junk, okay? And when we showed them these maps, they changed their tune quite a bit. And so, and it was relatively primitive. It had a flux gate compass and an altimeter from West Marine, literally. We had long baseline acoustic nav. We had a scanning sonar, ping, 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 with a stepper motor. But we proved the point, okay? And one of our skeptics actually on the ship was a scientist from Iceland called Carl Grunwald. And he said, after we got this all going and we were turning on these maps, he says, I don't have maps this good of Iceland. So he was a convert. And we were working with John Sinton from University of Hawaii and Belen Cormier from Lamont. And they churned out some fantastic papers with this data, and we've never looked back since then. Here's where we were, Southern East Pacific Rise, fantastically interesting, fast-spreading ridge. We sailed out of Easter Island, which is a whole fantastic experience in itself. Again, we had some great papers come out of that. We worked on the domed part of the ridge and then the rifted part. If you ever get to go to sea with John Sinton, that's what you'll do. You'll go to some really cool part of the world and you'll march down the ridge and work on segments of dramatically different ages. So it's like a little bit of time travel. So totally cool. We did that with him a couple of times. This is another trip that we did with Abe on a place called the Lost City, which is on the Mid-Atlantic Ridge, which is fantastically interesting because it has a completely different type of hydrothermal venting than the normal ones that are powered by volcanism. These vents are powered by a geological process called serpentinization, where mantle rocks and seawater interact to produce heat. And so we had the privilege to be on the follow-up expedition after the initial discovery, and we mapped it with our we had a real multi-beam on Abe at that point. And long baseline acoustic nav. And we made these maps, which were very important because they allowed our collaborators, in particular Jeff Carson and his postdoc, to figure out why this strange place had this type of venting. The basics of, if you have serpentinization, the rocks are expanding. So any sort of venting tends to be self-sealing. So it was never believed to be, even though everyone knew it could make heat, it wasn't seen as a place where you could have venting. But under some circumstances, there is these particular kind of faults where the venting can be sustained. And the Lost City was the first one discovered with our good collaborator, Deb Kelly from University of Washington. Here's the track lines. I love doing this stuff. This is like really fun, and we had a lot of time there, so you could see that we had a lot of time to go over it again and again. And so every day Alvin would dive, and every night we'd put Abe in and make the survey a little bit better. And here we are over the actual Lost City site itself. Fantastic stuff. Okay, we did a lot of work with our AUVs on hydrothermal vents, and in particular, finding new ones, and the way we did, and so why did people are so excited about this? There's a lot of reasons that hydrothermal vents are interesting, biological, chemical, whatever. One of the big reasons is that they provide clues as to mechanisms that are going on beneath the surface where we have no other way of measuring it. There are also significant inputs into the chemistry of the ocean. So finding more vents was Abe's job probably for 5 or 6 years, and we got to go all around the world and search these out. Working with our good friend Chris German, he came up with this scheme where we would every hydrothermal vent, like a power plant on a cold day, it has a rising plume. The hot stuff is light, and then it cools, and it finds a happy place where it spreads, the so-called non-buoyant layer. Well, the non-buoyant layer is real big, so you want to start looking for the non-buoyant layer, look for the biggest thing first, and then work your way down So we would do these surveys in 3 phases. We would start up in the non-buoyant plume and find the most attractive spot based on optical backscatter and redox potential. And then the next dive would be about 50 meters off the seafloor, and we would run the multi-beam and we'd make a fine scale map like you see there. And then the third dive would be flying at about 5 meters height, and we'd take photographs of the vent. And we did this, I wouldn't say all over the world, but we did it a lot of different places. I'll show you a map in a second. And this is something that Mike Jakuba and I did in 2004, where we actually did a fully adaptive survey. And the way we did that is we surveyed over the site one time, and then automatically, because we didn't even have any acoustic comms to the vehicle, it would then pick what it thought was the best spot and go back there and do a really tight near bottom survey there. And I've seen a lot of people doing machine learning algorithms for directing AUVs and vents, and they're fantastic, really nice, very elegant pieces of work. I don't think they do better than this. Anyway, that's just my opinion. So we did get to go all around the world. The stars are where we found new vent sites with Abe, Lao Basin, East Pacific Rise, Southern Mid-Atlantic Ridge, and the Southwest Indian Ridge, sailing with our Chinese colleagues. That was a trip of a lifetime, I have to say. Fantastic experience from every perspective. We did finally lose Abe after 222 dives. That was off the coast of Chile. Still, I get sad when I think about it. But one of the positives that came from that is Abe got an obituary in the New York Times, which was great. And we got email from people all over the world. Oh, we've been following Abe, and we're going down the pub after work today, and we're gonna have a little wake for the lost robot. It was great. But it was a bitter pill. But at that point, we had already built Sentry, which is this vehicle here, which incorporated many of the lessons that we learned from Abe. Because when we started building Abe, we really didn't know what our scientific colleagues were going to want us to do. So by the time we had 6 or 8 years of experience in with Abe, then we knew what we needed to do. Fly close to the bottom, fly up high, fly fast, carry a big scientific sensor suite, know exactly where you are, and run for as long as you can. That's what our scientific users want. Carry very flexible sensor payloads. And then, of course, we work with ROVs like Jason. In this particular cruise, we were on the Roger Revelle, which is, of course, a fantastic ship. And there's where we were off the northeast coast of New Zealand. Fantastic volcano, working hand in hand with Jason. I'll talk a little bit about that. Here's the track lines. I programmed all those myself, and I just love doing that. Okay, there's some cool things about what you do there. You're laying down a grid. The grid has to be somewhat conforming to the terrain for the vehicle to do its best job. So you need to do that, and that's why. And so we use those kind of I don't know what you call it exactly, but it's kind of like a grid, but it's bent because it's kind of following the terrain. But you don't want the vehicle to be turning all the time. You want it to fly in a straight line, but you want it to follow the contours, and you have to kind of make that trade-off. Then you need crossing lines. Everybody who's taken Larry's course understands that. And you need to link to the previous dive, and you may need to go back and do some repairs on some missing lines from the previous dive. So those are the criteria that go into this dive planning. And if anybody wants to make an automated algorithm to do this, please come talk to me. It would be really a fun project. And you see the quality of the multi-beam that we got was really good, and that was using MB systems. Thank you, Al. And especially all of the post-dive correction, navigation adjustment stuff works really good. So anyway, one of the big themes is the fusion of the ROV work and the AUV work is really important. So as we're making the map, the science party is using those maps to plan the next Jason dive. From our bathymetry, we generate underlays for the navigation displays that are used by the pilots. They put the mission plan right on top of that map, the pilots can zoom in and out and see everything. We do that both for Jason and for Alvin, and it's really tremendous. I have to say that in 1999, when we made those first maps with Abe, we'd bring Abe aboard at about 4 a.m. I'd make the maps, print them out on a piece of paper and hand them to the people getting in the sub. We've refined that quite a bit now, and it's really nicely integrated. The navigation systems match absolutely as well as they could. And Bruce Strickrott, who's the chief Alvin pilot and really runs that program, he told me, you know, I always look out the window. He said, but I could just drive off your map. But I never do. But I could. So it's really great. And these modalities go really well together. Because, of course, the ROV is only going to visit maybe 1% of the site. So which 1%? Where is the high value science? The AUV map is the way that you do that, the way you get that. Of course, many of you know with Alvin, it does some really great work. It actually can do some mapping itself, but mostly it takes 3 people down and they operate very sophisticated samplers and instruments. In this case, it's the isobaric gas tight sampler, which gets these absolutely pristine samples of the vent fluids, the hottest part, and it holds those in a gas tight, constant pressure isobaric little chamber and brings that back. And that is liquid gold for the geochemists. It's also the sampler that we used on the Macondo well, on the broken BP oil well, to get the gold standard samples. And that contributed to the Clean Water Act fines that BP had to pay. That crazy kind of nerdly contraption put billions of dollars into the US Treasury, okay, because of its role in determining how much oil BP had spilled into the Gulf of Mexico. So here's a little bit how things would work. In the old days, they would plan the Alvin dives with the multi-beam made from the ship, which of course is fantastic, but it's of limited resolution at the scale that you would like to carry this work out. And this was from 2010, so we actually do better than this now. But now the chief scientist plans the whole dive and hands that, and then that goes into an underlay. The pilots have that, the science party has it very much in real time. They know exactly where they are, what they need to do next. Very productive. Of course, this is not my work, but I know it's a very much interest in our theme of climate. Putting AUVs under the ice, Hanumat Singh's work, Andy Bowen, Chris German, and Mike Takuba with a NUI, Nereid under ice, and this Al Pluteman working with Remus vehicles under the ice. There's fantastic work going on. Our UK colleagues putting Bodie McBoatface, there's a whole great story there, and understanding what's going on with the ice shelves, the whole dynamics of that. Fantastic application for robots, and of course the Nereid under ice. Great. You want to go to 11,000 meters, you'll get more headlines if you take people down there, but if you want to get science done, we think the remotely operated vehicles are the way to go, and we did that in 2009. Of course, human history, there's a lot of it on the seafloor, shipwrecks, sunken cities, whatever. And so why is that important? And very, very briefly, shipwrecks are cool because the ships were the greatest technology of their time, so the ships themselves are of interest. But for many archaeologists, what's really of interest is what they tell you about ancient trade routes, therefore the ancient economy. So you can find out who was trading with who, when, where were the things coming from. Their ability to take objects recovered from shipwrecks and turn that into a story is amazing. If they have copper, for example, they'll tell you what copper mine that came from, okay, through isotope analysis. Okay, if you have some granite, they will tell you what quarry that granite came from. Okay, so you can tell the whole story. Where is the ship? Where did it come from? Maybe where was it going? Of course, how old was it? All those things can be determined. And so for many archaeologists, that's the big prize. For some archaeologists, the ship is the prize. Okay, and of course it's all interesting knowledge. Of course, the granddaddy of all shipwrecks, There's a Titanic. I was on the expedition in '85 when we discovered it, and we've had quite a it's the 40th anniversary of the discovery. It was a couple of weeks ago, so I had to convince people that was really me. It was a long time ago, and I don't even fit in that jumpsuit anymore. I was thinking about wearing it today, but and of course the famous boiler shot. That's the shot that we were sure it was the Titanic because we hadn't even found the hull yet. We had found the debris field, but we could see the boiler. That's actually a 35 millimeter still picture. The picture that we saw in real time was from a very fuzzy low light level video camera called a SIP camera, but it was clearly recognizable, and that was really great. So anyway, that's really great, but jumping almost 40 years ahead, this is not our work. I wish it was. This is done from Atlantic Productions and a group called Magellan. They took hundreds of thousands of images with 2 ROVs over a course of 2 weeks, all beautifully navigated. The images are all, the perfect distance, perfectly lit, and they fused them into this 3D model. You can literally walk around the wreck of the Titanic. I think it's going to be a touring exhibit, and I'll be buying a ticket right away. You can find a National Geographic special on it online. It is a fantastic piece of work. This is the future of doing any kind of shipwreck archaeology, to go down there and create these 3D renderings. You can see things in this that you simply can't see. The laws of physics do not let you swim up to the hull and look down the length of the hull. You can't see that far, okay? Whereas with this, you can. And so I'm imagining they're gonna do a touring exhibit. It will be absolutely fantastic. And they have the whole debris field, they have the whole thing totally, the whole digital twin idea, fantastic. So I always say, I take no credit for finding the Titanic. It was my second cruise. I was there to learn, okay? But what did I learn? Okay, the lessons from Bob Ballard and Jean-Louis Michel, who was leading the French effort. Okay, you need a detailed plan and the discipline to stick to it, okay? Your emotions take over if you let them. And every faint little thing off the edge of the side scan, oh man, that must be it, let's turn. No, you make a plan, you stick to it. That's how you succeed. Okay, you define and bound the search area. Ballard did that with Jean-Louis. Okay, define your target, come up with a sensing strategy. Ballard was not looking for the hull, he was looking for the debris field. Okay, and that's why we were primarily relying on cameras. There's no way you're gonna tow a video camera through the Titanic's debris field and miss it. And the Titanic's debris field is over a mile long. So why look for the ship when you can look for something that's actually easier to distinguish, maybe. We didn't know what the hull was gonna be like. But Ballard knew there was gonna be a big debris field. So, and then you gotta get the needed technology, and you get there for enough time that you can actually complete your search. And the number one rule, don't stop for maybes. Keep track of them, and if you actually get to the end of your search area and you haven't found it yet, then you go back to the maybes. If you sidetrack on every maybe, you may not get to the prize. So that's a big lesson that I learned. The public impact, that's a fantastic story. The reaction was overwhelming, but unanticipated. Woods Hole management wanted nothing to do with this project, okay? I was at meetings and they said, Bob, you've got a grant from the Office of Naval Research, just do what they want you to do, go out and test your equipment, and we'll see you when we get back, okay? Well, when our director looked out the front window and there were 100 reporters on the front lawn, that was when he decided it was probably time for him to get involved. And so, now that Hui is always waving the "We Found the Titanic" flag, it's a little bittersweet for some of us, actually. Now, I have to say that our whole team, it wasn't just Bob and Jean-Louis, okay? It was a whole team. It was the crew of the Nor. It was a big Hui project, okay? But it wasn't an institution project, okay? And finally, the next thing is, Hui, the Titanic really is a gateway for directing the public's interest to the deep sea. And I'll just tell you one more very quick story about that. A couple of days after we found the ship, you remember we had very limited communication back home. I was talking to one of my friends who was a National Geographic photographer, Emery Christoph. I said, and I knew that he'd been talking to his boss over the single sideband radio. So I said, Emery, did we make the papers? And he looked at me and he said, try the front page of every newspaper in the world. I said, oh, you know, and it was a surprise. Nobody knew how the public was going to react to this discovery. Pretty interesting. Okay, on to the midwater ocean, which is what I've been spending the last decade of my life on. Fantastic, a subject for many, many talks all on its own. You know, we have the euphotic zone, which is where there's enough sunlight to support photosynthesis. We have the midnight zone, sometimes called, where there isn't even any light we can measure. And then there's the twilight zone, which is between those two. There's light we can measure, but not enough to support photosynthesis, primary production. Early on, oceanographers thought there wouldn't be much living there. Now we know most of the things that live in the ocean live in the twilight zone because they can play tricks like migrate to the surface at night, where they're presumably at less risk of getting eaten. Of course, fabulous animals live there. And it plays a big role in the carbon cycle, okay? You have photosynthesis, so CO2 and sunlight make organic carbon, and then some or all of that is probably sequestered into the deep sea through many, many different complicated mechanisms. So unraveling that whole story is a big part of getting our climate models to work properly. And of course, there's a lot of existing technology, nets and acoustics and a lot of things. But we decided to build a new robot called the Mesobot. And we work with our colleagues at Embari at Stanford and the University of Texas, Rio Grande Valley. And the idea is it can track animals and it can sample and it can carry all the other cool sensors, but it's made for midwater. And I'm just going to show you just one little snippet of this video. This is actually Mesobot automatically tracking Oceanographic jellyfish. That's kind of cool. And we have a nice paper on that if you're interested in science robotics. And then this is another video I don't think I have time for, but I can send anybody the link for it. This is working with Mesobot and EV Nautilus. And I'm just going to skip forward and show you a little bit of video because that's what you want to see, right? Oops, that wasn't. I'm going to slide this forward. Yeah, that's what you want to see, right? This is Mesobot's view of the world. You know, its lights do attract animals. When we run white lights, we also run red lights. That happens to be a circulant worm, actually, I'm told. And we have you know hundreds and hundreds of hours of this kind of video. We see everything from these small animals like krill. That's a salp. We see siphonophores. We see squid, and we see some big.
What's the scale of that?
A couple meters across. Okay. I'm just going to skip forward, and you can see our friend. Oh, yeah, and then you can see our friend the Drix. We use Drix as an alternate mothership, just like Nautilus. From our point of view, from the Mesobot ops, they've become completely transparent as to which vehicle is serving as the communications link, the navigation platform, and then our colleagues all over the world have the same access through Drix to the vehicle that we have on Nautilus. So that's pretty cool. And I think it's really kind of revolutionized things. We do a lot of eDNA work with Mesobot, environmental DNA. That's where you don't actually capture an animal, you capture trace eDNA particles basically from the water, which allows our colleagues in biology to study the biodiversity. And we can do that under great control, and we have the video to go with it. We have all the other oceanographic sensors, and we have a whole bunch of really nice publications. Of course, trying to be mindful of the time here. Light rules the midwater. And so we have some very sensitive radiometers on the mesobot. We can measure down to about 600 meters. In fact, we have two of them. We put an attenuator on one so we can measure from daylight down to about 600 meters. And I think that's about 11 or 12 decades in terms of irradiance. And we can make mesobot follow the light just like the animals do by tapping into that in real time. This plot you see in the top, it's the sun is setting. See that the top plot is the surface irradiance. The irradiance that mesobot sees, so mesobot dove down, grabbed the irradiance at one level, and then as the sun set, mesobot started rising, holding that irradiance almost constant. It's pretty cool. So, and that can then be a platform for studying the movement of the animals during that. So that's kind of a cool engineering trick. And then here's our big picture setup: Nautilus, Drix, mesobot. Again, mesobot doesn't care if we're using the Nautilus or the Drix. Pretty cool. We've also done I'm very proud of some of the public engagement we've done. If there are any little children in your life, I highly recommend this book. It's about exploring the ocean and a whole lot more, and you should get it, and you'll know what I mean. But of course, all of these activities, it's really about people. There's our old AVE team from a long time ago. Mike Jakuba is still very active at Hui. Everyone else is retired in that picture except for me. Here's our mesobot crew. We were down in Bermuda during you know what. We did some really great work there, and I'm very grateful. All those folks showed up and worked super hard. It's great. Before I finish up, I always got to get my acknowledgements in. We had the Ocean Twilight Zone project, NOAA, Ocean Exploration, and of course, all of the folks at home, my family, for tolerating our crazy lifestyles. And in closing, I'm going to show you this. This is the latest Hui kind of pride piece thing. Let's see if we can make this work. Oops. Does it have a button? It's a, oops. What did I do wrong there? Oh, here we go. It's not gonna, let's not worry about that. We can not show that. That's just kind of a cool thing that Hui came up with. It's a little bit inspiring. You can find it online. Anyway, with that, I think I'll close and have some time for some questions.
Questions, please.
Hi, thank you so much. That was really fantastic. One of the first things you talked about is you said you had some strong thoughts on the biomimicry.
Oh yeah. I think there's a tremendous amount to be learned by studying how animals work. The idea that that's actually the right way to make a vehicle, I think, is pretty much unproven. And I would even say, it's a fantastic project to make a humanoid robot to go in the ocean. Okay, it can't do most of the things that our non-humanoid robots do. Pick up really big, heavy things. So I think I understand that it's really interesting to understand how animals do what they do. Okay, how do fish swim? How to cephalopods? How do they swim and whatever? And how do they camouflage? And all these things are tremendously interesting and useful. I'm certainly not speaking against that. Okay, but making an AUV that looks like a fish, to me, doesn't make any sense. Motors and propellers, they work really well, okay? and I've heard people say, we can make them more efficient. I go like, more efficient than the Ambari long-range AUV, which has like 80+%, measured joules coming out of the battery and compare it to drag force times velocity. It's like 85%. Okay, you're gonna do better than that? And then when I look at those vehicles, I go, okay, I've seen a lot of underwater vehicles. Where does the really big battery go? Because like, that's the first thing, we literally build our vehicles around the battery packs. Right, and they're like, yeah, well, I think we can fit a battery in there somewhere. You're like, no, you're missing the point. It needs big energy storage. Unless you say, oh no, I'm gonna make it eat like a fish. So it doesn't have to carry all its energy, it can get it. Okay, great, okay, go solve that one and then maybe you have something, okay? But again, I'm not trying to be a stick in the mud about cool stuff. And I'm not trying to claim that, we know all the answers. But to look at that as some kind of a holy grail kind of answer to the problems, I don't think that's actually true. Despite the fact, I have a bunch of friends that worked in the how to fish swim problem, and they did really great work. And that's very interesting and useful. And I'm sure it will find some application, lowering drag or making some clever mechanism. But I don't think we're gonna have AUVs with fishtails, frankly. Anyway,
Thank you.
just my opinion. Yes,
What kind of sensing and odometry methods are you using to ensure that your AUVs are maintaining the paths that you set?
okay, something like Sentry uses bottom lock Doppler, which is like a miraculous invention, and an INS. We combine those in kind of the simplest possible way. We don't do the full inertial navigation solution. We basically use the INS as a incredibly high performance gyro in pitch and roll. Okay, and we temper the information from the Doppler velocity log with that. Okay, that gives you a relative track on the bottom. And then post dive, we use the ultra short baseline system from the ship in a kind of a big batch mode to then make sure we know exactly where that is on the seafloor. But a vehicle like Sentry actually doesn't know where it is on the face of the earth as it's driving. It only knows its relative track. And that's how we've programmed it. So we literally drop it in a certain place. We make a correction if we need to based on what we can see from the surface. And then literally it runs on its own. We almost never correct it during the dive. We could through the ACOMs, okay? But the Doppler INS solution is so good that we almost always, we just let it run, okay? That we do a correction at the end, after we recover.
Does it respond to like a sudden current or something and try and course correct?
Oh yeah, the DVL is totally on top. I mean, if you swam down there and pushed it sideways, it would find its way back onto the track, because the DVL would say, oh, I just moved sideways. And the DVL works surprisingly well, even in really bad terrain, like you saw the terrain that we run that in, okay? Those sensors are overcoming enormous challenges. You think the DVL has 4 beams, okay? Well, when you're on flat bottom, it's pretty obvious what that means. What does that mean when the bottom is coming up and down and creeping in from the side and between the algorithms from the manufacturer, and then we do some processing on that after the fact. It works really fantastically well. The number that a lot of people throw around is that you can do with a decent Doppler inertial system, you can do about 0.1% distance traveled. Some people claim even better than that. I'm not sure that's true in really bad terrain, but that's a pretty good number. 0.1% is a meter in a kilometer, right? Did I get that right? Yeah, that's amazing. Imagine if you closed your eyes and walked a kilometer and you knew where you were within a meter. That's pretty good. And that's from off-the-shelf instruments and just applied really, really cleanly and, getting all your time skew out and all those little gremlins that we have to deal with.
Thank you.
Yeah. Yes.
Repeat the name of the book that you recommended and also.
Oh, it's called.
That fantastic video, is that available?
Yes. Where the Weird Things Are is the name of the book.
That's right.
If you go onto the WHOI website, you go to our shop, you can find it there. If you just search on the Mesobot. If you search on Mesobot book, you'll find it. And we have it at the bookstore, on our website. You can also get it on Amazon. I'm directed to the WHOI website. It's actually extremely well done, and they give you fast delivery and whatever. And and I always say, when Friends had a baby, they used to make way for ducklings. Okay, that famous book. Okay, now they get the Mesobot book. Okay, and I'm very proud to say that I think that's great. Yes.
Just wondering, are you aware of other robots that are similar to Mesobot, like being specifically designed to explore?
Yeah, Chris Roman is building something called the Vampire at URI. I don't know too much about it. I know that he is being super careful about making it even stealthier than Mesobot. The thing that's not stealthy about Mesobot is the thrusters. Okay, we have the quietest thrusters we know to put on there, but they're still, you can hear them in the video, okay? So Chris is trying to use variable buoyancy and some other things like that, but I haven't seen a published report on it, and I haven't gone down there to visit him, which I should do. So I do know about that, and so it's, vehicles for midwater, the stealthiness comes from hydrodynamics, from acoustics, and from the light. So I didn't show you any of our red light video, it's actually pretty good. And you may not know this, but most midwater and deepwater animals are blind to red light. Because the ocean is a blue-green filter. So if you use red light, you probably influence the animals either by attraction or avoidance less. In fact, biologists know more about the capabilities of marine animals' eyes than you could possibly believe. I played around in that literature for quite a while. It's fantastic. Almost all midwater animals, they only see in the blue-green because that's what the ambient light is. So literally, they have no capability for seeing the other wavelengths. Pretty cool. 490 nanometers. That's what they all see, and that's whether it's a fish or invertebrate or whatever, they all get the same answer through the miracle of evolution. Yes.
Any more questions? Do we have questions?
Yes, we have 2 questions
Okay,
online.
great.
So from Daniel, we have how do we account for the effects of underwater current on these vehicles to make sure they maintain the right heading?
Oh, okay, that's almost the same question we talked about before. If the current pushes a vehicle, let's say a vehicle like Sentry, which has its bottom lock working, if you don't have the bottom lock, now that's a big problem, okay? But when you have bottom lock, then it has a direct measurement of its velocity in 3 dimensions relative to the seafloor. So if the current is pushing it sideways, it'll figure that out. If it gets pushed off the track, it will then, using a classic line of sight type control algorithm, it will then vector itself back to get back on the track. So, and that does happen. And so the answer to that is the INS gives it almost perfect knowledge of its attitude, true north. And then the Doppler velocity log gives it very accurate data about its relative motion in the seafloor, including any side slip.
He also had a follow-up. Do these vehicles have enough endurance for long time missions?
Let's see. I think the champions of that are probably the Mbari long-range AUV, which has done like a month. Okay, Sentry can probably do like 20 hours maybe. And now there's variations of the Remus that can do many days. And then there's commercial vehicles like a Hugin that can do better part of a week. So there's been a lot of progress on that front.
And then we have another 2-parter from Louise. Do Do you see potential for integrating acoustic methods on AUVs to monitor the dispersion of hydrocarbons or other pollutants in the water column?
Yeah, we've done a fair amount of work with, I'm trying to think of, there's been some work around seeps and plumes, both natural and oil spills, using different kinds of sonars. We did a flow rate measurement on the Macondo well. I was part of a team that did that. That and that sample that I talked about, those were two of the big elements that went into the estimate of how much oil they had actually spilled. Actually not oil, hydrocarbons, right? Remember, it was a witch's brew of everything, natural gas, all kinds of stuff. So the simple question of how much oil did they spill is actually a super complicated question. So we used a Doppler velocity log in a kind of a acoustic Doppler profiler mode. We used a scanning sonar, and it was all precisely navigated and controlled. So yeah, we have methods for that. And there was other work that was done that was kind of following up on that, where people did experiments in natural seeps. So, you can't make your own oil spill, that's not allowed. So you go to a natural seep and try to measure it. That's not a perfect experiment because you don't have the perfect control that you would like. But yeah, no, the sonars can see, they can certainly, people in this room know, sonars even from the ship can see natural gas seeps, and work right down there in this building on that topic. Fantastic discoveries, and actually quantifying those can be done with the sonars, and then depending on the scale of it, you can use higher frequency sonars and get closer.
And the second part to that question is, what are the current challenges in using AUV mounted multi-beam systems for high resolution mapping in Arctic or deep sea environments?
Well, that's done all the time. My first recommendation would be to take the CCOM multi-beam course if you want to do that. I don't think it's so specifically oriented to doing it from an AUV, but all those lessons apply the multi-beams work great on the AUVs. The more stable the vehicle, the better. And again, things like having the inertial navigation system is huge because that allows you to bookkeep any sort of wobble on the vehicle really well. And of course, then everything we talked about, how you localize the navigation on the vehicle, that all contributes to the map quality. And then finally, we have really nice tools to exploit the overlap between crossings and overlaps that's why that Hover volcano map that I showed, you can't see the track lines in there, okay? And that's because we exploited the overlap to match up all the tiny little features. And we have some great tools to do that. And of course, the sonars have evolved. Every couple of years there's we don't build the multi-beams ourselves. We buy them from Kongsberg or, whichever vendor, Rezon, there's a bunch of them. They're excellent and getting better all the time.
Daniel did have a follow-up to the endurance vehicles, sorry.
Yeah.
If there was a trade-off between the different, I believe if I understand this correctly, the duration of these the long-term missions as such, like a couple days to a couple hours, if there was any trade-offs between those vehicles, or if it's just battery capacity?
Yeah, let's see. Battery capacity is a big thing. Propulsion efficiency is big. If you actually do like a sort of a budget on a vehicle like Sentry, the multi-beam itself draws a lot of power. I think most of the power though is in the propulsion. So, a vehicle that's more streamlined than Sentry would do better. But on the other hand, a vehicle like Sentry is designed to be able to get good multi-beam imagery even in very difficult terrain that's going up and down. So, vehicles that have to pitch to go up and down, you pay a price for that because unless you have a multi-beam that can electronically compensate for that. The multi-beams we have now, they can compensate for roll, right? They do that. You can plug the roll into the side of the thing and it beamforms the roll out, okay? Am I right? Yeah, that's an awesome thing, right? Better to correct it kind of at the source than correct it after the fact. I don't know that any that do that for pitch though. They have that, they do for pitch as well.
Some do, yeah.
Yeah. So that's obviously a huge factor, and when we first started using multi-beams, literally, we got the multi-beam and then we applied the pitch and roll correction to it. That's the second best way to do it, right? You really wanna do it at the beamforming level, which the sonars now can do. And then that's beautifully matched to these fantastic inertial navigation systems that we have.
We have one more from McGee's again could AUVs play a role in monitoring subsea carbon storage sites or hydrogen production systems, particularly in offshore environments?
I'm sure if you look at all of the things we're doing to map out seeps and plumes, hydrothermal plumes and BP oil plumes, Sentry did it. I didn't even talk about that. We mapped out the big neutrally buoyant plume at about 1,000 meters that was coming out of the broken well there. I think all of that work is directly applicable to any kind of carbon, storage kind of scheme. But the people who are sponsoring or were sponsoring that work, they seem to want to do something without direct measurement though, so I don't quite know what I think they've maybe watched too much Star Trek. But, they want that thing where Spock tells the captain, oh, here's the carbon flux, and I don't know anybody who knows how to make that. But people are trying, right? Could you use acoustic methods? I don't know. Sounds like magic to me, but.
And then finally, with the increasing volume of data from AUV missions, what are the biggest opportunities and obstacles for applying AI, ML in processing and interpretation?
Okay, I think there's lots of opportunities there. Let me think. I think, these vehicles produce so much data that you can drown in it. Okay, so I think a lot of that, the AI can be very useful in terms of helping people understand complicated data sets and picking out the things that are most of interest. Or things where, two different looks at the same thing are a little out of illustration and then that can be fixed. These are the kind of things that when I say that we fixed, when we did all the post-dive corrections on that multi-beam data, that was me with a mouse and a little bit of help from the computer, matching up all the crossings and the overlaps and all that, and taking out the last couple of meters of navigational error. I think algorithms that can be smarter about that would have prevented me from getting carpal tunnel on that trip. Literally, I did. It's kind of the worst case, you're just so zoned in, right? And you're just so focused, and then you realize, oh shit, I haven't gone to bed in, a day. My arm really hurts, okay? So automating stuff like that, or the planning, I think is another thing. I just gave you some little snippets about when you plan those complex dives, what goes into it, this trade-off between flying a straight line and following the terrain, fixing the holidays in yesterday's survey, linking to yesterday's survey, having the crossing lines that let you do your corrections, your patch tests, if you will. being able to just throw the existing ship-based multi-beam map in there and having those track lines spit out would be totally cool. Anybody wanna work on that? Just give me a call. I've got all the raw data for you to work on it.
Yeah, awesome. Yeah,
Alrighty.
thank you so much, Nancy.